Hello, today we will discuss about field effect transistors. In this lecture, I will cover junction field effect transistor and metal oxide semiconductor diodes. Field effect transistor is a 3-terminal device. We have 2 terminals, source and drain, and in between these 2 terminals we are controlling the current flow by using the third terminal called gate. So, applied voltage on gate produce a electric field, and this electric field will affect the current between other 2 terminals, source and drain. So, we can control the carrier flow between source and drain by using the third terminal gate. There are many forms of field effect transistors such as metal oxide semiconductor field effect transistors, junction field effect transistors, high electron mobility transistors. But if you see the working principle in all these devices is same. So, here in the figure you can see we have 3 terminals, source, drain and gate. So, between source and drain we are controlling this carrier flow by using the third terminal gate. So, first I will try to explain the basic working principle of field effect transistors. So, let us consider a 2-terminal device, and the IV characteristic of this device is non-linear. So, we can define the current ID equal to, this one is the some function of our applied voltage Vd, and if we bias this device by using some external battery, voltage is E and here resistor E is R. So, in figure A you can see the circuit diagram, and now we can define this one by using the equation E equal to ID R plus Vd. And if you will plot these 2 equations, here you can see in figure B, these 2 equations will cross at a point, and at this point the current is ID and voltage is Vd. So, in steady state from this device we will get the current ID and voltage is Vd. Now, in this device if you will add the third terminal, here you can see in the figure A. So, here we have added third terminal, and if you will apply some bias on third terminal, now we can tune the current between other 2 terminal A and B here. So, here in figure B you can see the characteristic. If you have not applied any voltage on third terminal, this one is the gate, then we will get the same IV characteristic similar to the 2-terminal device. Now, if you will apply the voltage on this one, this voltage will affect the carrier flow between these 2 terminals. So, this current we can increase or decrease, this one is depend how much voltage we are applying and what is the polarity. So, this one is the basic principle of field effect transistor. In field effect transistor we are tuning the output current by applying some voltage on the third terminal. We can use field effect transistors for amplification and switching application. So, here we have to apply the small voltage on gate, and this small voltage will give the large change in output current, this one is the drain current. So, if you compare this field effect transistor with bipolar junction transistors, so bipolar junction transistor is a current control device. Our output current is depending on the input current, how much input current we have applied, but field effect transistor is a voltage control device. Here the output current, drain current, this one is depending how much voltage we have applied and what is the polarity of applied voltage. Now, I will come on the junction field effect transistor. So, here in figure A you can see the structure of junction field effect transistor. We have the source and another terminal is drain, and between source and drain this carrier flow we are controlling by the third terminal, this one is called gate. So, this one is the simple structure. We have the channel, this one is N doped, and then we are making 2 junctions by doping highly this holes doped P plus and another in the bottom side P plus. And now, by applying this gate bias we are controlling the channel width. When we are modulating this channel width, our output current will also change, because output current is depend what is the width, what is the cross section area of our channel. So, here in figure B you can see the here channel width, this one is the magnifying view of this channel. So, here if you see we have the two junctions, one is the top junction between P plus and N, another one is bottom between P plus and N. Now, here in the channel voltage drop you can see in the below figure here. So, source we can take, this one is at reference, and now we are applying with respect to source some voltage on the drain. So, here voltage drop is increasing and maximum is near to this drain point. Variation of channel width with 0 gate bias. If we will not apply any gate bias, in that case we will see how our current voltage characteristic. So, here we have not applied any gate bias, and now our source is we are considering as a reference, and on drain we are applying some voltage. So, here this channel is the end of, so electron will flow from source to drain. So, current will be in opposite direction from drain to source. So, if you will apply the small drain voltage, in that case in small drain voltage here channel width is very small. So, we can consider here our current will follow the Ohm's law, V equal to IR. So, current linearly will increase with the voltage at low voltage. So, this region is called the linear region. Now, if you will increase the voltage in the drain side here this junction is in reverse bias, but between source and gate applied voltage is 0. So, in the source side here this junction is in thermal equilibrium, but in drain side our junction is in reverse bias and the depletion width is there. Here you can see in the figure B, here in figure B this depletion width is increased. So, basically channel width is reduced. So, now here the resistance is there, this one is increased. When we increase the resistance, this current voltage characteristic will depart from the straight line and this will try to saturate. So, in figure B you can see near the pinch off. So, near the pinch off our channel resistance is very high. So, this will here if you see V equal to IR, if resistance is high our current will not follow the straight line. Once this depletion width, both depletion width up and down will pinch at a particular point, this voltage is called the pinch off voltage and current is the pinch off current, saturation current. So, we will get in the current at the pinch off voltage we will get the saturation. Now, if we will increase the voltage our depletion width will change, but in towards the source side, but here already the resistance is there, this one is maximum. So, current will saturate. So, in this case we have not applied any gate voltage. Now, if we will apply the gate voltage, what will happen? We will see here. So, here in figure A you can see the this biasing, we have applied the gate, here negative bias we have applied on the gate, and now we can see the current voltage characteristic between source and drain. So, here if you will increase the VD, ID is also increasing and then saturating. And when we apply the negative bias, when we are applying the negative bias, now the pinch off is happening at the lower voltage. So, here if you will apply for example -1 volt, here this one is our ID current, this will reduce -2, -3. So, again if we are increasing the voltage, our channel current is there, this one is decreasing with gate voltage. And in right hand side figure you can see the circuit symbol of this device. So, now first we have to calculate the pinch off voltage, how much voltage we have to apply, and this voltage is depend on the channel cross section area and also depend on the channel doping. So, here in figure you can see the Hx is the channel half width at a position x. So, here you can see the coordinate directions in x, y, z. So, basically our from source to drain total distance here we have taken, this one is the L. So, our metallurgical half width of channel is A. So, total width of channel is 2A, and here depletion width is changing from drain to source. At source side this one is minimum and maximum is at drain this one. So, now the channel width is also changing, and we can consider this one is the linear variation from source to drain, and now Hx is the channel half width at position x. And here in the below figure you can see the voltage drop, and we can consider in a short channel we can consider our voltage drop is also increasing linearly. So, source is at reference and we are applying some Vd voltage at drain. So, this one is increasing linear. So, we can take one small slice in this one, the width of slice is del x and here position is x, and another here x plus del x on the slice width. Here we can calculate the depletion width at the drain position by using the same PN junction. We have calculated this one. So, here in the thermal equilibrium the depletion width W at x equal to L is equal to 2 epsilon s VBI upon QD Q and D and square root. Here epsilon s is the permittivity of semiconductor, VBI is the built-in potential at the junction, and ND is the channel doping, and Q is the charge. This depletion width is in thermal equilibrium. Now, if we will apply the reverse bias, here our built-in potential will be VBI minus GD. So, by using this one we can calculate the depletion width at different applied bias. Since VBI is negligible compared to this gate drain voltage, so we can neglect here. So, our depletion width W will be 2 epsilon s minus VGD upon Q and D square root of this one. So, here at the pinch off, here our voltage will be Vp will be equal to minus Vgd, and if we see at the pinch off our Hx will be 0. So, we can calculate the depletion width will be equal to W equal to A. If we will substitute these W equal to A and Hx equal to 0 here in our equation, here in equation 1 we can calculate the pinch off voltage. So, pinch off voltage Vp, this will be Q A square Nd upon 2 epsilon s. So, pinch off voltage is depending on the cross section area of channel, also depending on the channel doping. So, by changing this one we can design, we can fabricate junction field effect transistor of different pinch off voltage. IV characteristic of junction field effect transistors. Here in the figure you can see once we will reach at the saturation our current is constant with applying bias, but before this saturation here if you see this one is increasing current is increasing with applied drain voltage. So, here we can write this equation. This calculation is little bit complicated in this case, but by using the Shockley equation we can calculate this one and we can define the transfer characteristics. So, here ID equal to ID SS 1 minus VGS upon VP square. Here ID SS is the saturation current and VGS is the applied voltage with respect to source and VP is the pinch off voltage. Here if we see our current will follow the square law. So, these devices also called a square law device. The junction field effect transistor can be used as a variable resistor because here between source and drain the resistance is changing. This one is depending on the gate voltage. As VGS become more negative, the resistance increases, otherwise resistance is very low in the conducting state and in off state resistance is very high. Now, we will discuss about the metal oxide semiconductor diodes. MOS diode is the heart of MOSFET, the most important device for advanced integrated circuit. The MOS diode can also be used as a storage capacitor in integrated circuit and it forms the basic built-in block for the charge coupled devices. Here you can see the 3D and cross section view of MOS diode. So, in MOS diode we have the metal, we have oxide and semiconductor, and generally the thickness of oxide is few nanometer. So, first we will see the energy band diagram of ideal MOS diode. at 0 voltage. So, we have not applied any bias. So, in thermal equilibrium we will see the energy band diagram, and here we are talking about the ideal diode. So, ideal diode means at 0 applied bias the energy level in semiconductor and metal, the Fermi level is there, this one is the constant. Second, there is no carrier flow from metal to semiconductor, from semiconductor to metal. That means the oxide resistivity is infinity. And third, when we apply some bias, we give some charge to metal, same charge will be generated in the semiconductor side. So, magnitude of charge in semiconductor and at metal will be same, only polarity will be different. When we will apply the negative bias on the metal, here Fermi level will shift towards up, and this will create the charges on the semiconductor surface. So, we have applied negative bias, so positive charge will accumulate on the semiconductor surface, and here this surface we can calculate these charges by using this equation P equal to Ni exponential Ei minus Ef upon Kt. So, here our semiconductor is p type. So, Fermi level is close to valence band, and Pp means here holes concentration in p type semiconductor. So, now if we will increase the hole concentration, from this equation we can see the difference between Ei minus Ef will increase, and for ideal MOS we have assumed that there is no carrier flow from metal to semiconductor, from semiconductor to metal. That means our Fermi level in semiconductor will be constant, this will not change. If Fermi level will not change, that means difference between Ei and Ef will increase. So, here Ei will move in this case towards up. So, here you can see in this figure the Fermi level, intrinsic Fermi level, conduction band and valence band. With respect to intrinsic Fermi level, here conduction band and valence band will also shift towards up, and this case is called the accumulation, because at the surface already our semiconductor is p type and now more holes are accumulated on the surface. So, by using this one we can calculate the holes concentration. Now, if you will apply the positive bias on the metal, in semiconductor side here negative charges will generate. Our semiconductor is p type, so holes will deplete from the surface. When holes will deplete here, these holes will leave the ion behind this one, and we can consider this one is similar to the p-n junction. So, here one depletion region will form, and this case is called the depletion region. And again if we will increase the voltage, here the Fermi level, intrinsic Fermi level Ei will come below the Fermi level. In that case the surface layer is inverted from p type semiconductor to n type semiconductor, and this case is called the inversion case. So, here our semiconductor is p type, but surface is behaving like a n type semiconductor, and here we can see the energy band diagram, and we can calculate this electron concentration by using this equation Np equal to Ni Ef minus Ei upon Kt, because the Fermi level is constant and now Ei is coming below the Fermi level. So, here on the surface this will behave as a n type semiconductor, and this width of this inversion layer is very small, generally 1 to 10 nanometer. So, initially the surface is a weak inversion condition, since the electron concentration is very small. The strong inversion occurs when the electron concentration near the surface is equal to the substrate doping. So, if electron concentration is equal to the substrate doping, substrate is p type, then we call now this inversion case is called the strong inversion. The surface depletion layer width reaches at the maximum at the strong inversion condition, and we can calculate here in the semiconductor total charges Qs equal to Qn plus Qsc. Qsc is the charges in the depletion region, and since in the strong inversion our depletion width is maximum, so we can calculate minus Q Na Wn. Here this you can see in the equation. Now, I will come on the analysis of the surface depletion layer. So, here you can see the energy band diagram, and here we have defined the electrostatic potential, and in the bulk semiconductor electrostatic potential is 0, and the difference between EI and EF is, we can define this one is Q psi b. Psi b is the difference between Fermi level, intrinsic Fermi level and Fermi level, and at the surface potential is equal to psi s. This one is called the surface potential. So, now we can calculate the electron and hole concentration in terms of electrostatic potential. So, Np equal to Ni e की power q psi minus psi b upon kT. Similarly, for holes you can see on the screen, and at the surface the densities we can write Ns. This one is the electron concentration at the surface, and Ps is the hole concentration at the surface. And by using these equations, so here the energy level EI and EF we have replaced by the psi and psi b, and at the surface potential is psi s. So, based on this surface potential we can divide into 5 categories. In first one, if surface potential is psi s is less than 0, so this one case is called the accumulation of holes, bends upward. Second case, when psi s is equal to 0, this one is called the flat bend condition. Third case, if psi s is greater than 0 but less than psi b, this one is called the depletion of holes, bends downwards in this case. And if psi s equal to psi b, this one is mid gap. Here the electron and hole concentration both are equal. So, we can say this one is the intrinsic concentration region. If psi s is greater than psi b, this one is called the inversion case, bends downwards in this case. So, now we will calculate the depletion width in the strong inversion case and the charges inside the semiconductor. So, by using the piezo equation, here you can see on the screen del square psi upon del x square equal to minus rho s x upon epsilon s. Here rho s x is the charge density at position x, and this we can define rho s equal to minus q Na. So, this one is depend on the doping of substrate. By solving this equation, we can calculate the electrostatic potential, and this will come psi equal to psi s 1 minus x upon w and square of this one. So, here by using this equation, how electrostatic potential is changing inside the semiconductor, we can derive this one. And here psi s is the surface potential, and this one is equal to psi s equal to q Na w square upon 2 epsilon s. So, here the surface is inverted when psi s is greater than psi b, and in this case, in the strong inversion case, as we have defined, the electron concentration is equal to the hole concentration of substrate. So, for strong inversion, Ns we can take equal to Na, since Na is related to the psi b, and here on the screen you can see Na equal to Ni exponential q psi b upon kT. So, by using these equations, in the strong inversion case, our psi s in inversion will be equal to 2 psi b, and psi b again related to the doping of the substrate. So, here we can write this one psi b equal to kT upon q ln Na upon Ni. So, by using these equations, we can calculate the maximum depletion width, and this one is depend Wm equal to square root of 2 psi s inverted upon Qa. So, finally, if we will substitute the psi s inversion value in this equation, we will get here the depletion width, and this depletion width is depending on the doping of substrate. And if you know the depletion width, now you can calculate the charges in the depletion region by using the Q SC. This one is the depletion charges in the depletion layer is equal to minus Q Na Wm, and this will come equal to minus square root of 2 Q Es Na and 2 psi b. So, by using this one, we can calculate the charges, and here you can see the maximum depletion layer width versus impurity. If you are increasing the substrate doping, here the maximum depletion width is there, this one will decrease. We have discussed about the device structure, working principle and current voltage characteristic of junction field effect transistor. Also we have discussed the structure, energy band diagram and surface depletion analysis of metal oxide semiconductor diode. I hope you have enjoyed the lecture. Thank you very much.